The cosmos, vast and mysterious and full of secrets. For millennia we've gazed at the stars, wondering, where did all this come from? What rules govern it? Among the universe's greatest mysteries is a hidden force, the cosmological constant. It's an energy woven into the fabric of space itself, shaping the fate of everything. This isn't just a scientific curiosity, it determines whether the universe expands forever or collapses. Understanding it is key to understanding our place in the cosmos. Our journey will take us from Einstein's mind to the edge of the observable universe. We'll uncover how this invisible energy is accelerating the universe's expansion. The story of the cosmological constant is the story of the universe itself, a tale of mystery, discovery, and human curiosity. Fasten your seatbelts, the cosmos awaits. Imagine balancing a pencil perfectly on its tip. It seems like an impossible feat, doesn't it? It's practically impossible unless you invent a force, something unseen, that pushes up from below with just the right amount of pressure, perfectly calibrated to counteract gravity's pull. That's the essence, the core concept of the cosmological constant. It's a bit like that invisible force, but on a cosmic scale. It represents a cosmic push, a fundamental energy inherent in space itself, constantly working to counteract the relentless pull of gravity. The universe, as we observe it, is filled with matter, galaxies, stars, planets, and everything in between. And gravity, that universal force, relentlessly pulls it all together, attempting to clump everything into a single point. But what if space itself, the very fabric of existence, pushes back against this gravitational collapse? What if there's a repulsive energy woven into the structure of space, an energy that doesn't weaken or dissipate over vast cosmic distances? This, in essence, is the cosmological constant. It's a concept that attempts to quantify this mysterious energy. It manifests as a constant pressure, an outward force that drives the expansion of the universe, stretching the cosmos like an inflating balloon. Gravity, as we know it, constantly tries to pull everything in, drawing matter together through mutual attraction. But the cosmological constant, in opposition, pushes everything apart, driving galaxies away from each other at ever-increasing speeds. It's crucial to understand that this isn't a force emanating from any specific object or location. Instead, it's a fundamental property of reality itself, intrinsic to the very fabric of space-time. The cosmic stage itself, the arena in which all cosmic events unfold, is actively stretching and expanding. This expansion is what propels galaxies away from each other, leading to the observed recession of distant cosmic objects. Interestingly, the cosmological constant wasn't originally conceived to explain the expansion of the universe. Its initial purpose was far more conservative, to create a theoretical model of a universe that was perfectly static, neither expanding nor contracting. The cosmological constant was imagined as the perfect counterbalance, a precisely tuned force to perfectly neutralize the effects of gravity. It's a simple yet incredibly powerful idea born from a desire to understand the fundamental forces at play in the cosmos. It suggests that space itself is not merely an empty void, but an active and dynamic entity, constantly influencing the behavior of the universe. And this seemingly simple concept would ultimately revolutionize our understanding of the universe, forever changing the landscape of cosmology. Back in 1915, Albert Einstein, a name synonymous with genius, revolutionized the world of physics with his groundbreaking theory of general relativity. This revolutionary theory proposed that gravity isn't just a force, but rather the warping of space-time itself, caused by mass and energy. Eager to explore the implications of his new theory, Einstein applied his complex equations to the universe as a whole. But he soon encountered a significant problem. According to his calculations, gravity, acting on all the matter in the cosmos, should inevitably cause the entire universe to collapse in on itself. However, the prevailing scientific view at the time was that the universe was eternal, existing in a steady state for all time. It was believed to be static and unchanging, a cosmos in perfect equilibrium. To reconcile his theory with this widely held belief, Einstein introduced a new term into his equations, the cosmological constant, often represented by the Greek letter lambda. This constant represented a hypothetical repulsive energy inherent in space itself, designed to counteract the attractive force of gravity. By carefully selecting just the right value for this constant, Einstein could create a model of a static universe, one that neither expanded nor contracted. It was a universe held in perfect, delicate balance. In essence, it was a mathematical adjustment, a theoretical construct not directly supported by observational evidence, but rather motivated by the prevailing belief in a static and timeless cosmos. The cosmological constant, therefore, served as a kind of fudge factor, artificially propping up the universe and preventing its predicted collapse. With this addition, Einstein had seemingly rescued his theory from predicting the universe's untimely demise and brought it into alignment with the accepted cosmological wisdom of his time. However, little did Einstein realize this seemingly arbitrary fix would eventually become one of the most profound and important concepts in modern cosmology. As it turned out, the universe had a surprise in store for everyone. The cosmological constant was far more than just a convenient mathematical trick. It held a crucial clue to understanding the true nature of the cosmos. And before long, mounting evidence would compel Einstein to completely rethink his model and reconsider his assumptions about the universe. In the 1920s, astronomers like Edwin Hubble discovered that galaxies are rushing away from us, the universe is expanding. This shattered the idea of a static cosmos and made Einstein's fix unnecessary. His original equations, without the cosmological constant, had already predicted an expanding universe. Einstein realized he'd missed a historic prediction, calling the cosmological constant his biggest blunder. The term was discarded, seen as a relic of outdated thinking. For decades, physicists set it to zero, focusing on whether gravity would eventually halt the expansion or not. The universe was expanding, gravity was slowing it down, and the cosmological constant faded into obscurity. The big question became, would the universe expand forever or collapse in a big crunch? Einstein's abandoned idea was relegated to a footnote in science. But the story wasn't over. The cosmological constant would return, in a way no one expected. The universe had one more surprise in store, and it would change everything. For most of the 20th century, cosmologists operated under a certain assumption. They thought the universe's expansion, born from the Big Bang, was gradually slowing down. It was envisioned like keys tossed in the air, rising against gravity's pull. The central debate within the scientific community was whether gravity, the great cosmic binder, would eventually halt the expansion altogether, leading to a big crunch. Or, alternatively, if the universe possessed enough initial momentum to overcome gravity's relentless tug and expand forever into an increasingly desolate future. But in the late 1990s, a series of groundbreaking observations by astronomers measuring the distances to distant supernovas, specifically Type Ia supernovas, began to challenge this established view. They found something shocking. The universe's expansion wasn't just continuing, it was speeding up, accelerating at an ever-increasing rate. It was as if the cosmic brakes designed to slow the expansion had failed catastrophically, and the accelerator was floored, sending the universe hurtling outwards at an unimaginable velocity. Some mysterious, previously unknown force was overwhelming gravity's influence, acting against it on a cosmic scale. This force was actively pushing galaxies apart, driving them away from each other faster and faster with each passing moment. Scientists desperately needed an explanation, a theoretical framework to account for this bizarre phenomenon. They began to consider the possibility of an anti-gravity force, a repulsive energy inherent in the very fabric of space itself. And there, waiting in the wings, almost forgotten, was Einstein's cosmological constant, a term he had introduced and then famously disavowed. His blunder, once considered his greatest mistake, suddenly became the perfect candidate, the leading contender, for explaining this unexpected cosmic acceleration. The ghost in the machine, the cosmological constant, had returned from exile, not as a mere mathematical mistake or an artifact of flawed reasoning, but as a real, measurable, and undeniably influential part of the universe's fundamental composition. The cosmological constant was back in the spotlight, now recognized as central to our understanding of the cosmos and its ultimate fate. Einstein had been right all along in a way, but for reasons and implications that he could never have imagined in his wildest dreams. The universe was not just expanding at a steady pace, it was running away from itself, accelerating into an unknown future with increasing speed. The cosmological constant, or something very much like it, was the engine driving this runaway expansion. And with this realization, the mystery of the universe, its past, present, and future, only deepened further. What does cosmic acceleration mean for our future? For billions of years, gravity slowed the expansion, allowing galaxies to form. But as the universe expanded, gravity weakened, and the cosmological constant's push stayed constant. About 5 billion years ago, the balance tipped, cosmic acceleration began. Now, galaxies are being pushed away from us faster and faster. In the far future, most galaxies will disappear beyond our cosmic horizon, their light never reaching us. The night sky will grow emptier, leaving our local group isolated in a vast void. Future astronomers may never know other galaxies existed. The evidence of the Big Bang and cosmic expansion will vanish from view. We live in a unique moment, able to see our cosmic origins before dark energy erases them. It's a sobering reminder of how precious our perspective is. The universe's fate is being written right now. Picture the universe as a loaf of raisin bread rising in the oven. The raisins are galaxies. The dough is space-time. Early on, gravity, the dough's weight, slowed the rise. But imagine a magical yeast everywhere in the dough that keeps pushing outward, no matter how much the bread expands. This magical yeast is the cosmological constant, or dark energy. As the dough expands and thins, gravity weakens, but the magical yeast's push stays strong. Eventually, the yeast dominates, and the bread expands faster and faster. That's our universe today. Dark energy is driving an accelerating expansion. It's a simple analogy, but it captures how dark energy shapes our cosmic destiny. Today, we call the cosmological constant dark energy. It may be constant, or it might change over time, we don't know. We call it dark because it doesn't interact with light and because its nature is a mystery. Observations show that about 70% of the universe is dark energy, 25% is dark matter, and only 5% is ordinary matter. Most of the cosmos is made of things we can't see or explain. Unlocking the secret of dark energy is a major frontier in physics. Is it truly Einstein's constant, or something more dynamic? New telescopes and surveys are mapping the universe in unprecedented detail, searching for answers. Understanding dark energy could revolutionize physics, linking the largest and smallest scales. The quest continues, and the stakes couldn't be higher. We began with a mystery, a force shaping the cosmos. The cosmological constant, once a blunder, is now the engine of cosmic acceleration. If dark energy remains constant, the universe faces a lonely, cold future. A big freeze. If it changes, we could see a big crunch or even a catastrophic big rip. The fate of everything depends on this invisible energy. We look up, armed with knowledge but still facing deep questions. What is dark energy? Is it a simple constant, or something more? The answer lies in the light of distant galaxies and the afterglow of creation. Our quest to understand it is a testament to our need to know our place in the cosmos. The next chapter of the universe's story is waiting to be discovered.